Give it a moment over here for Twitch. Twitch, if you are there. I have no camera today. Hopefully, I didn't break the audio as well. If you could let me know if you can hear me, that'd be fantastic. Although, once you just start the stream, nobody is there. So, bing, bang, boom. All right. I'm going to assume they can hear me. So today is the 8th of October. We're halfway through. I got it right this time. Dynamic allocator misuse here in CSE466. I actually still had it wrong. I just had a few minutes to fix it right before the stream. Memes. So one of the things that people hopefully realized is they kind of moved through the first half of the assigned content or the module was just because the challenge like asks for a secret, it doesn't necessarily mean that you need to get the secret. You have to think about not what the challenge is necessarily asking you for, but what is the implemented details of what is the challenge doing. One of the examples here, and I don't know what level it is, it asks you for the secret, but based upon kind of the primitives and things that you have, it's not easy to leak out the full secret value. There is an easier approach where instead of using the heap to generate a pointer and read something or leak something, you could use the heap to generate a pointer. Hello from Sierra Leone. That is a far ways away from here. Um, you could use that pointer to, for instance, overwrite the secret value, at which point the implementation of the comparison is just checking two memory addresses. So you know what it is, despite the fact that you didn't leak it because you overwrote it. Hopefully, that was a solution that many people ran into. It's not the only way to solve that particular challenge, but definitely a good meme. It came up a lot in office hours and recitations that I showed up to. Other memes here, general success strategies. Asking on the Discord seems to be helpful. I'm speaking less, but you all seem to be chattering a decent amount. So I'll let you help each other so then you can get extra credit. Because if I respond, then you don't get the opportunity to earn the extra credit. And then some people are asking about safe linking, but that was far enough out that I was just like, whatever, I'll wait on that. For understanding the heap, based upon last week, we saw GDB is useful. You can get the equivalent of the kind of help text challenge printouts. Now, when it comes to working on the heap, there's kind of a couple strategies. You can spend some time thinking about how this stuff works, or you could just like, do the 10,000 monkeys pounding 10,000 typewriters and maybe Shakespeare comes out the other end strategy, which some people certainly do. And if you solve the challenge that way, there's not much I can do to stop you from doing that. However, the meme is correct. In the long run, it will bite you because you need to be a bit more methodical about what you're doing in the later challenges. And this last meme over here kind of brings up the general um, idea of some of the problems and things that we have thought about before. For instance, a buffer overflow. Does a buffer? I don't know the challenge in particular. I didn't actually look to get context here. But is a buffer overflow part of this challenge? It's not. So you need to get I imagine, the saved return address, right? You're trying to corrupt that to ROP or something along those lines. And when we played around with that on the stack, we were always fighting this canary thing. Why was the canary not a problem here? Okay, so the comment for the class, I got or Twitch, I got a different mic here, so you probably can't hear anything. Was because once you have a stack leak, you can calculate whatever you want. So you could just calculate the location of the return address on the other side of the canary. Hello from Molly. Okay, we're just going all over the place today on Twitch. And this idea of getting a pointer that points to anywhere that you want is something that's known as like an arbitrary read or an arbitrary write, right? You're getting an arbitrary pointer. And it's a very common technique in like the greater world of exploitation, where one of the things you really want to get is be able to get the program to return you a pointer to any memory location that you define. And once you have that ability, things like buffer overflows are no longer a factor because we aren't limited by moving linearly through memory. I keep saying there's this extra credit thing. There's at least some proof that things are getting to the point where extra credit can show up on the grades page. So right now there is a leaderboard thanks command that spits out some data that isn't properly sorted and filtered, but it gives you right now what it's showing is the number of unique messages that were thanked by user this semester. So from the beginning of the ASU semester. But then it's sorted by total thanks because I can't write code. Uh, yeah, it happens. So it's a small, simple bug. I'll get that fixed later tonight, and hopefully the extra credit will also be live because that's tapping the same data source. It's the same table in the implementation. So that should just be a nice, easy thing to switch on. But I didn't want to do it right before class started in case I caught everything on fire and like blew away the database, and caused unnecessary problems. All right. Demo plans. I crossed it off, but are you stuck on anything in particular? I believe most people are somewhere around like 13 to 16, is kind of what I got the general feel for. Is that accurate? I got a hand wave. Is a hand wave yes? It is inclusively 13 to 16? Okay. Okay. I'm on 12, but I know how to do it. So I just got to get to the other side of it. So somebody here on Twitch says something about finding address offset level 11. So that is an amazing question that doesn't actually ask anything. Get the flag. There's no camera, but I gave you a thumbs up. The meme here uh, is relevant and hopefully something that you figured out already going through the first half. How do we get these arbitrary pointers? There's a general pattern for if you have a use after free. So if there is a program that isn't nulling out pointers after calling free on them, you call malloc malloc. That gives you two allocations, assuming these are the same size. So malloc malloc, free free. That puts two things into the T cache. You then overwrite the second allocation that was freed because that's going to be the one that is at the head of the T cache. When you overwrite those first 8 bytes, you're overwriting the next pointer. Then you malloc twice, and you will obtain a pointer automagically from the heap to whatever value you wrote on the next pointer. Very, very, very common pattern. Hopefully everyone figured that out. Some of the later challenges there play with this idea a little bit more, where we may be doing, for instance, 3 mallocs, or we need to have more pointers. Otherwise, other than that, we're just doing some math and figuring out where things are in memory. So hopefully that's on board. About performing that action, I can demo it, and you can tell me if you want me to waste the time or not. Malloc malloc free free overwrite malloc malloc. That is how you get an arbitrary read or an arbitrary write. You have the pointer, whether it's an arbitrary read or an arbitrary write. Depends upon what you're doing with it. Can I call puts? Can I call scanf? Can I call read? Can I call write, etc. But once you have the pointer, it's just what are you doing with it that determines whether it's a read or write. What most people will probably spend the better part of this week stuck on is something called safe linking. Who here has gotten to level 16? Okay, we're not there yet. That's you don't know the joys that you're about to experience here. Okay. So I didn't change my demo binary, so it still has whatever that bug is where I'm not exploding on reading and writing a null pointer. One of the things that you'll see on level 16 onward, if you look at the challenge directory, is there is this lib folder. You do not need to interact with the stuff that is in lib. If we take a look at challenge lib, what you'll see here is there is a libc, and then there is a version of the loader. Uh, the way that these So if we are in the dojo and we type uname A, this challenge environment is currently, what does it say? Ubuntu, I think it's 2004. Oh, that doesn't say it. I need LSB release. Okay. LSB release. This is Ubuntu 2004. So this is a pretty old version of Ubuntu. It's still current. It's an LTS. So you still like can find this out in the wild. But the the libc version that is packaged with an operating system is limited by the version of Ubuntu. So that means that the Ubuntu 2004, if we were to look at my a.out, this is going to go to the libc that is part of the challenge. And if we were to check what version that is, which one way, I know people had some like crazy fancy thing, but you can just run it. And it will tell you this is libc 2.31. So 2.31 is kind of the latest version of libc that is packaged with Ubuntu 2004. This is a great version of libc to learn how the heap works, but it is not what we would call current. If we take a look at the libc version that is located in this challenge folder, it says 235. So I believe this is what's packaged with 2204. And at this point, we're on 2404, so there is a newer version of libc. But at the time I last built this, that was current. And one of the changes that was implemented here is something called safe linking. Everyone remember how my original toy binary worked, where I had all these options? We could malloc, we free. Cool. So I have it's the exact same binary. I literally copied it, except I ran a command called patch-elf, which allows you to change what library a binary will try and use dynamically. And the challenges work the same way. So that challenge baby heap level 16, it is hard coded or patched such that it will reference the libc that is in, where is it? It says it here somewhere. Challenge libc. And so it's going to not be using the stock libc version. Okay. So let's run this safe linking guy. Let's try and do that same thing that we saw already. Malloc, free, overwrite, malloc. See if we get something. Malloc 1 will go size 20. I'll malloc 2, size 20. I'm going to free 1, will free 2. And then we said we want to write something. Oh, I need probably IPython, GDB. We got to get fancy here, don't we? This is the same thing we had before. But I can't write an address there. Whatever. I'll use the challenge binary because it'll be easier since it has help text. Okay. Malloc 1, 20. Malloc 2, 20. Free 1. All right. I want to stop right here and just take a moment. We need to make a mental note that the head pointer is 32C0. So I freed 1. When I free 2, what would we expect the next pointer of the newly freed thing to be? It should be we push to the head, so the next pointer should be whatever is currently at the head, right? It should be this 32C0. Is that what we see? This is no longer 32C0. And if I were to, for instance, Malloc 1, 20, Malloc 2, 20, Malloc 3, 20, Malloc 4, 20, free, wow. That's why you script. Malloc 1, 20, Malloc 2, 20, Malloc 3, 20, Malloc 4, 20. free 1, free 2, free 3, free 4. What happened to my help output? I just freed 4 things into this guy. It says, well, it shows me 2. How many are actually in the T cache? How do you know that? Is the count wrong or is this printout wrong? The printout's wrong. Why is the printout wrong? Is T cache? It should have 4. We know we have some idea of how the T cache works. And the way that this, like, super nice help thing that we have in this challenge works is it's literally just looking at the Tcache per thread struct. It's looking at the head pointer. It's assuming these are valid addresses. And it's just saying, all right, cool, show me whatever's there. All right, cool, show me whatever's there. And I showed that these addresses, as I free them, 2C0, 2C0, the next pointer is now no longer what I think it should be. This is something that's called safe linking. Safe linking is a way of obscuring the next pointer and making it so that we can't do what we did in the first 15 levels. Because now whatever I write here is going to be invalid. There's some type of encoding, XORing, mangling going on. Another thing that you'll notice with this libc version, it's not safe linking specific, but it's done around the same time. We had this key value before, and this key value corresponded to a location on the heap, right? There was a pointer, if I remember right, to the tcache per thread struct. Does this look like a valid pointer? No. With a newer libc version, the key isn't really a key. It's now just like this randomized random 8 bytes that you just have to know, right? And so now it doesn't even have meaning. We can't leak the key to get a heap pointer, and we can't even leak the next pointer. Like, even aside from overwriting it, if I were to print that, is that a valid memory address? Probably not. It might be, actually. But that's because I have PIE disabled. It's definitely not the correct pointer that I want. So how does safe linking work? Safe linking boils down to 2 things. There is a location. This is a location. This is a value or a pointer. Technically, it's a mangled pointer. The way safe linking works, and we can find the source, I'm going to call this mangled pointer, is you take the location bit shifted by 12, you XOR it with the mangled pointer. Did I get it right? 12, 3, 8, 8, 4, 12. Okay, so that's 300. Let's see if I got it right. I didn't get it right. Gosh dang it, safe linking. Which one did I grab? 320. What? 3 down 1. EA 300. Yeah, okay. So I did. Okay. I did perform the operation correctly. I just wasn't paying attention to which value I was getting it from. Okay. Now, safe linking is confusing and it's messy. And the best place to look for it is the libc source or my amazing lecture slides on this. So there's 2 because I have the link to the source right here. There's 2 functions that happen. There's protect pointer and reveal pointer. Now, when a pointer, like a next pointer, gets stored, we must protect it. It's doing that same thing I just did in Python, where I called it what? Location and then mangled value, right? It's taking They're calling it position instead of location. Bit shifting it by 12. What is the relevance of a 12-bit bit shift when we think about memory addresses? So when we talked about like ASLR, right? What parts, what nibbles were randomized? Right. The least significant three nibbles are a constant offset into a page. And so what's happening here is we're saying, hey, the least three significant nibbles of this address, those are constant. I don't want any constants in this mangling, in this obscuring process. So we're going to take the address of where this pointer is. We're going to get rid of the constant bits. So that way, the least significant byte is an ASLR byte. Does that make sense as far as why we're shifting by 12? Cool. Then we're going to XOR that with the pointer itself. And that's what gets written to disk. Now, when we need to reveal a pointer, right? So when the heap needs to, it gets this mangled mess thing, which is what we see over here. It does exactly what I did. It's going to take, it defines reveal pointer as protect pointer with the address of the pointer and the pointer, which makes sense. That's the location, that's the pointer. So we are doing the same operation. It's reversible because it's an XOR. So what two pieces of information do I need at face value to kind of reason about this thing? Right, I need the position and I need the pointer. Right? How can I get the position? How can I get these values? So the position is the question was where is the position? The question says, am I on YouTube? Yes. Go on youtube.com/pwn.college. It's going to be the same things as what's here. Normally, there is a camera. I just failed hard today. Apparently, I lost what I was doing. Location, minor. Okay. Have that. How did I lose that whole thing? Okay. Malloc 120, Malloc 220, Malloc 320, free 1, free 2, free 3. Okay. So the question is how I say we're currently saying I need the location and I need the pointer, right? And the question I posed was how do I get these values? Well, what does malloc return? A pointer, right? So if I have something that leaks or I can print the literal value that I'm getting, I have it. But how do I know what this location is? So what determines where this gets written? Where I forget I don't have a camera, you can't see me. It's the order that I free stuff, right? The first thing that I free, I think I did three here, which is a shame because you can't see the third. But I freed the second thing. Its address gets written to where the next pointer should be, which is the address of the most recent thing I freed. So in theory, if I get if I have access to the pointers that are returned by malloc, I could know the location and I could know the pointer value. But if I already know the pointer value, do I really care? No. The whole reason I would need this is to get to the pointer value, right? So I could know the location and have the mangled value, and I could do what I just did and turn a mangled pointer into a real pointer. Okay, that's cool. Uh, in practice, you don't get both values. In practice, the only thing that you could leak is what we've done already, where we have this next pointer, right? And we can overwrite it or we could puts it. So in practice, we only get mangled pointer. Does anyone think this is reversible from just the mangled pointer? It's okay if you haven't done your XOR, your logical operations, and it actually takes some deep thinking to get to the other side of this. The answer is yes, it can be done. So XOR is reversible. Okay, so how do I get the okay? So the statement was so XOR is reversible, and I get this mangled pointer, but how do I get the other thing that it's being XORed with? And the trick to this entire thing relies on two properties. Okay. First, hopefully you've realized or found, as you've messed around with the first half of the heap here, that the heap is generally speaking deterministic. If I malloc 10 things that are 64 bytes in size, it's going to go for, what would that be? 80 byte allocations. And it's going to be, I can know where these allocations are. Yeah. And we also know the heap is on one page of, well, not necessarily one page, but it starts at one fixed base address, right? So we're working, there's actually a lot for a fresh heap. There's going to be a lot in common, actually, between the pointer and the location of the pointer. Okay? So that's one key observation. And we can see that just looking, I have to look at head instead of, I don't know if I what the order that I freed these in. I have to look at head instead of down here because this is the mangled stuff. But we have the actual pointer is 1678 2C0. What is the next pointer? 1678 2E0. What's my third pointer? 1678 300. There's actually a lot in common between these two values, isn't there? Now, this challenge in particular, I was a little confused when I fired this up to just take a quick look. Uh, this is a pretty small value for a heap pointer. It's because PIE is disabled because I'm not trying to make it harder than it needs to be. Uh, right? If PIE was enabled, these heap addresses would be a bit longer. And in turn, things would get more messed up. But we can think about the math here the same. So if this is my mangled guy, and the correct pointer, what he was, could be 2E0. Are there parts of this that are in common and not changed? Yeah, there are. Take a look at this. We have to think about this piece by piece. So if there are parts of it that aren't changed and everything is shifted by 12, what the most significant 12 bits or three nibbles would be the same. Okay, because that didn't get XORed. But what else do we know about those most significant three nibbles? They're the part being XORed. So let's see if we have the technology. So if I say I need an ad, let's grab a real address for this thing. 2E0 is located here. So this is my location. All right. So we have three real values I pulled from the heap. If I take the location bit shifted by 12 and we make it hex, there's a value. What happens if I take the valid pointer bit shifted by 12, make it hex? Okay, that's the same value. What happens if I take the mangled pointer bit shifted by 12? Hmm. Almost the same value. Uh, and so this is something that is the gotcha when we think about how to dereference this. I said there was an assumption. The assumption was that these values are all on the same page. right? If they aren't, when we do this bit shift by 12, we'll be off by 1. So this apparently rolled over to the next page on the heap, which is why that address didn't have the exact same value. But we could say, okay, maybe it's off by 1. We could try this, say it's even, try it -1, right? We +1. We could get to this, right? They're somewhere near each other. It's only a couple guesses away. So we can get this piece. We see that there's this similarity. Now, what's happening here is the location bit shifted by 12, and we are XORing that by the valid pointer, and this should be equal to that should be equal to my mangled pointer, right? So far we're just going in a circle. But this, the most 3 significant nibbles here are consistent here. And what's being XORed, so what that isn't getting XORed. What are these 949 getting XORed with? What did I do? Oh, these 4, 1, 2, 3, 4, 9498 is getting XORed with 1678 or 1679, depending upon what the location is, right? But we know that the 3 nibbles are 167. So could I take, what do I have there? OX9498, XOR that with 167, make it all hex. Okay, and then what did we get there? Mangled pointer, bit shift, location, 167. 167 is going to get XORed with, what did I do it with? Oh, I didn't do it with the, we'll go to my picture. I drew this all out. So somebody, this is why, um, like trying to show this is hard. I'll blast this out on the Discord as well. It's been on there for a while, but we have a mangled value and we're XORing it with the pointer bit shifted by 12, right? But what we don't know here is this page, right? We saw that the page in my thing could have been 8, could have been 9. We're just going to call it X because we don't know, right? We could be wrong. So we just kind of take a wild shot at that. And when we do that, we get, as I'm showing here, and I tried demo in Python, but it turns out this is hard to do in Interpreter Live. The most 3 significant nibbles are revealed, and the rest is good, except we have to account for where's that page. So how do we do this from just the mangled pointer itself? I have to define some terms. Okay. We know that the correct pointer is the mangled pointer XORed with the um, pointer bit shifted by 12. Pointer 12 is going to be these 2 things called mid and mid 24. Well, how do we get mid and mid 24? Am I on the wrong page? No, I am on the wrong page. So that's why this isn't adding up. Okay. I put them in the wrong order. All right. Pointer in position. The least significant nibbles of the position don't matter. DEF, right? The mangled pointer is the position, bit shifted by 12 bits, XORed with the pointer. So if we are only given the mangled pointer, which is this thing right here, then we can come up with this mangled 12 and mangled 24 value by bit shifting the mangled value and XORing with itself. So what we're doing is we're bit shifting by 3 here, and then we see there's another bit shift by another 3, right? Because every time that we bit shift by 3 and we XOR, we're revealing another 3 nibbles of the technically it's the interim value, and it gives us this mid value. So then if we take mid by mid 24, and again, this is just bit shifting and XORing itself out, things are canceling out, and we reveal the pointer bit shifted by 12. But what we don't have once we have the pointer bit shifted by 12 is the 3 most or least significant nibbles. We lost those, right? They were bit shifted away. So then if we take the mangled pointer and we XOR it with the bit shift, see if this will let me zoom in. And we XOR it with the pointer bit shifted by 12, we will reveal the least significant nibbles minus whatever we had when we guessed the page. Now, you don't have to understand all of this math, okay? This actually boils down to a pretty simple Python function. But all we're doing is this right here, which is actually on the slides, because a lot of this condenses down and eliminates itself. Okay, but the action that is occurring is we're taking the mangled and we're computing these intermediate values by bit shifting the mangled pointer by 12 and then XORing it with that value, and we're just repeatedly doing that to reveal more information about it. It unrolls itself except for the very last nibble. And then when you write all of these, mid thing is a mangled pointer that's being bit shifted by that amount. So that's why these are multiples of 12. I'm sorry, multiples of 12 because you're shifting by 3 nibbles and then you're shifting by, what is that? 24 bits. See if I could math 3 bytes. And these intermediate values cancel out to where you end up with just one nice little function, which becomes this, de-mangle. And we can write this in Python. And if you don't want to go through the math, I get it. That's why, oh, this doesn't show it on the slides. I'm a liar. So let's make a de-mangle function. Def de-mangle footer. I need to take that footer, I need to XOR it with itself, bit shifted by 12. So that's my first. And we're going to declare that mid. This plus offset, you're free to adapt this function as you want. That's accounting for that difference in page, right? Because if the location and the revealed pointer, the correct pointer, are on different pages, you're going to have to add or subtract 1, 2, whatever the difference in the pages on the heap are. And we return this mid value XORed with mid bit shifted by 24. So let's just finish that. We'll assume that we're on the same page. We'll type exactly what's on there. So now I have my de-mangle function. If I run de-mangle on mangled pointer, hopefully math works today. Did I call the other thing valid pointer? I could be off by the least significant, but here we see that we got, just with the mangled pointer, we're able to reveal the valid pointer. Now, if the pages were off, what I would get from this de-mangle function would be something like this. I would get 8 to E1 or 8 to EF, because this last nibble is where the guess of the page happens. Now, this was some hand wavy stuff. If we want to write it all from scratch, we can, but does this make some sense? At a bare minimum, you can steal this function and this will work, except for when it doesn't, because things are on a different page and you'll have to adapt this. Shouldn't the 8 change to a 9? You're saying this 8 here. So the answer is no, in the actual math. So you would successfully be able to, with this de-mangle function, right? So the scenario would be, give me a location. Okay. Uh, Oh, those are on different pages. Whoop. Oh, they aren't on different pages. Okay. Would be if I made location 0x61679300, right? That would be if the location was a different page. Then my bad mangled pointer would equal the location bit shifted by 12 XORed with my valid pointer. Do you agree? Okay. So then we try and demangle the bad mangled pointer, and let's make it hex. And so what we saw here is the 8 that was demangled was in fact correct. We were able to reveal that. And the only thing that was off as an effect of guessing the wrong page was this least significant nibble. And that doesn't make sense at like face value, right? But I liken it to peeling the layers of an onion, right? If we're only given this mangled thing, we bit shift it by 12 and XOR it with itself. You say no. You say yes. Okay. That's always going to trip me up, and I apologize. And so that gives us this intermediate value where we have revealed more information. We haven't revealed all of it, right? Because what we have here is the value, but it's still XORed with some other stuff. And so what we're doing is we are slowly revealing like 3 nibbles at a time, and then using that relevant piece to shift over and XOR with itself. And because of that, we can, the only place where the nibble that determines the page, right? The least significant nibble that determines the page, because we're bit shifting by 12, the location where that is getting XORed, that's this C right here. And so we don't know, we can cancel stuff out, but we always end up with this C, right? It's this unknown thing that I can't know. I can know every single nibble except for that least significant one. Now, if the heap is you're doing small allocations and you're starting at the beginning of a page, you can pretty reliably say these are going to be on the same page, right? I malloc, they come from the same page. I free, they're right next to each other. The next pointer is going to be stored on the same page as what it is referencing. Now, if you have a busy heap that is mallocing and freeing and it's allocating stuff of different sizes and it's freeing that back on, all of a sudden, like no holds bar, right? You can't even function with this assumption that these addresses are related to each other, right? Like you would have to start fuzzing further as far as guessing how far away these are, because on a heap that's been running for a long time and mallocing and freeing, you may have a allocation that's at the beginning of the heap, and may have an allocation that's 30 pages into the heap, right? And so then all of a sudden you don't know. And if you were 30 pages into the heap, it wouldn't actually just be this least significant nibble, would it? It'd be the first byte that we would have this kind of randomness property to it. You're saying the heap doesn't have to start at the beginning of a page. Is that true? Everything in memory. Oh, yeah, chunks can be wherever they want. So we see here that the heap is allocated a region between C9000 and EA 9000, right? Yeah, the chunks do not need have they don't care about pages. If you're allocating things that are big enough to where you care about pages, more than likely the heap will actually call mmap instead of returning some gigantic chunk. Now we see that there's a big range there, and we have no guarantees about what page a allocation or chunk is used from. The question? The question is, what's the size of a page? So a page is always on Linux is hex 1000, which is why we see that these least three significant nibbles are 000, and why we can have that assumption, like when you look at something in IDA, and we say things like, uh, I can look at the offset in IDA and it means something over in the binary, like in GDB or in the running binary. That is a side effect of how virtual memory addresses are used. Everything, the least three significant nibbles are always an offset into a page. Now, for larger regions of memory, when IDA here says this is at what is it, 2D9C down here at the bottom. That's the offset into the binary. The least three significant nibbles will always be valid. Anything beyond that is something that would have to be added to the base address of where this is loaded into memory, right? Which will be, in this case, that's going to be in the elf. And so if I were to try and find that over here, this is where my elf is. So I'd take this plus whatever that is, and that would get me to that location, right? But the reason that we can do that is because memory is always mapped by pages. That's why when we look at the VM map, these are always 0, and how we can reason about what's going on. It's 4096 in decimal, but hex 1000 is a page. Okay. So that was a bit messy, but that's what safe linking is. Levels 16 through 20, or at least 16 through 19, maybe 20. I don't remember off the top of my head, but 16 through 19 at least are levels that you saw somewhere between 10 onwards, like 10 to 15, and then repackaged with safe linking. Now, the level of impact that safe linking will have on a given scenario will be wildly different, right? Depending upon what you needed to do. What if I need to overwrite? I need to do what was on that slide over there. I need to malloc free write something and then malloc twice. I want to get an arbitrary pointer. What can I still do that? Someone says, yeah. What's different? I have to reverse engineer the mangling of the pointer. Okay, that's a fair statement. So I have to understand what value is going to be mangled. So can I write the next pointer? No. What do I have to write there? I have to mangle the next pointer. So if I wanted to write a next pointer, I thought I had a beautiful. I don't know how I keep losing IPython sessions. I'm doing something horrible here. So if my target where I want to get to is hex 1337, I need to figure out where is this next pointer going to get written. We'll use some valid address from right here. So how do I mangle my target if I want to write it somewhere. Location, bit shifted by 12, XOR, target. So this is what I'd want to actually write instead of the next pointer. And so now we have this like additional work that we need to do. Now, one of the other things that safe linking does is it makes sure that the least significant nibble of every, they call it revealed pointer, is 0. So one of the things that we could do, and we did do in some of the earlier challenges, is my target is at, I don't know if we did OA. Is that what we did to you? And then we could write this target to our next pointer. There was a problem with OA. All right, we solved that problem. And maybe we went to like O1, right? That's great. This could not be mangled by safe linking. So if I were to try and do that target, let's set my location back to what it was. We would do this same operation. When it gets revealed, which is going to be the same thing, but in reverse here, the heap implementation is going to check this nibble, and it must be 0. If it is not 0, then the heap will say, we've detected corruption because I never reveal a pointer that doesn't end in 0. So now we can't specify arbitrary locations. Everywhere that we specify must be a multiple of 16. It must be a mangled multiple of 16. Mhm. So the statement was I showed the math where you can end up with this least significant nibble being incorrect, right? So does that matter? Can you just do that math, and if you get it wrong, make it be 0? I'm fairly confident the answer is no, that will not work because of the way that the math breaks down. All right. You're going to say, I just showed you something where like the only difference was the least significant nibble. Um, but I want to say somewhere in there that that breaks down and you can't do that. Um, what's that? Yeah. So the observation was if there's more than a 16 page or 15 page, yeah, 15 page difference between the location and the pointer, then it would obviously impact the next nibble. I want to say there's something else in the math that will break down as well. Because I what I showed you was when it was valid and then when it wasn't. But if you go down that road, you'll I don't know. We'd have to math it, but I think you can't just make that assumption. So if you I malloc something, I free something, we'd have let's take a quick look at glibc source. So it's linked here in malloc.c. Oh, that's not 235. Let's at least look at the exact version. Like these are good questions. Everything you are saying, if I free something, what I am looking for is protect pointer. And what we see here is on free, it is not checking that. Right? But if we were to look at reveal pointer, which is the other side, there is this check for misaligned chunk. So I can free things in that don't end in zero. Yeah, but whenever the heap tries to reveal the pointer, it does this check to see if it's a misaligned chunk. And if we were to look at what is a misaligned chunk, oh, it's going to go even deeper. Looking at glibc source can be a little bit tricky. It's going to chunk to mem and then add it with this mask. Okay, it'll be in this mask then. Boop. Is whatever the malloc alignment is -1, and that's going to be what's bit shifted, which is going to be the least significant nibble. Just trust me down there. Like that's what's going to happen when this is checking for a misaligned chunk. Is if you find it in there, that's awesome. But it's checking for that least significant nibble here on the malloc. We're inside reveal pointer inside. Well, this is mal info. And find the other one. Is this malloc? Where am I? No, I'm in malloc C. You don't want to go. That's fast bin. This is Tcache. Okay. Tcache entries, reveal pointer. E key 0. It's on the malloc that it checks it because you'll get that. There it is. Okay. You'll get this. Well, no, that's fast bin. You'll get a malloc unaligned error that you'll sig abort is what'll happen. I'm failing to find it. Because there's actually a lot in the heap, right? There's all these other bins that I haven't hit you with. That's the definition. Now it's going to be reveal. That's fast bin. But if you just trust me, I don't want to just stare at glibc source. That the least significant nibble has to be 0 on the pointer, otherwise you'll explode. That's why you're exploding. Okay. So the safe linking makes some sense as far as what it's doing. Cool. You're gonna have a really, really rough time with it. People hate it. Even if you steal my handy function that I gave you there, it's gone. Is it def demangle footer mid equals pointer bit shifted by 12 XORed with pointer, and then we return mid XORed with mid bit shift by 20. Even if you have this function, there are going to be scenarios, and I know level 16 is one of them, where this function is not going to save you. All right, because you can't just run this function against what you're going to leak and get what you think you're going to get. And so you will have to have some understanding of what is the heap actually doing and how is it mangling things. Because this becomes extremely complicated. Here, all of these were valid addresses. They're all on the same page, give or take, right? They had a lot in common. What happens if I want to like throw a stack pointer on there? Are any of the assumptions that I made about things going to work out well? No, they aren't. And so now you're going to have to, okay, well, how does this thing actually break down? How does this impact my pointers? And what if I need to allocate more than one thing, or I need it to place a specific value somewhere, right? I need to use the heap to perform a write. Well, the value that I need it to write needs to be a permutation so that post mangling, it is the value that I want. So I need to demangle something that isn't mangled. So when it is mangled, it's the value I want that's there. This is these are some of my favorite levels and students' least favorite levels. I will say that despite it being a small number of challenges for this particular module, I do believe safe linking is going to make a reappearance here in 466. So if you skip it, you'll probably get hit with it again. So it is worth trying to tackle it. The nice thing is that once you understand what the mechanism is, you can reasonably just like automatically deal with it, right? If you want something that is more interactive, like a playable example, if we go github.com, shellfish, how to heap, this is a bit out of scope for this module, but there's one thing in here. This is what the follow-up heap that we aren't doing in this course touches on. Because all of these are various other techniques that interact with all sorts of different things inside the heap. What I'm looking for is there is one of these that says decrypt safe linking. Boop. Most heap exploits are explained given a proof of concept piece of code, which is some runnable piece of C code where they're assuming, based on the C code itself, that you have access to, for instance, a use after free, or you have some piece of information. They may or may not have comments. I personally am kind of 50-50 on how useful these are until you compile them and run them. But inside this repo is a runnable example of, okay, what are the values? How can we deal with it that's annotated? This is typically how you learn about how heap exploits work. Is somebody throws together a POC that looks like this. You stare at it, you print it, you look at it in GDB to try and understand what's going on. For this course, the only thing that we're doing heap related is Tcache, and so this is the only POC that matters. Is how do I decrypt safe linking? It's going to be the same thing that I showed here in Python, and the same thing that I'm scribbling out here in the math. Does anyone have anything else for me? I've got about 10 minutes. Yeah. And one of the challenges, the pointers are nulled after they're freed. Okay. So I don't, I strive to, even though I use 16 as a straw man here, I didn't actually try and look at it. I try not to solve challenges themselves. If if the pointers are nulled out, do the first thing I think of, and I don't know that this is applicable to whatever the challenge is, so you'll have to tell me. Do I have the ability to overread or overwrite? Okay, so if I malloc something that's 24 bytes in size, the expectation is the most I will write to this memory address is 24 bytes. Do I have the ability to write 100 bytes to this 24 byte allocation? Okay, so if I have the ability to overwrite, what we've really created is, ooh, let's see if Jeff does what I think it's going to do. Sudo GDB. Malloc 120, Malloc 220. We'll free one, we free two. We're in GDB. I have heap bins. Now, one of the things that the GDB plugins will do on the topic of safe linking is GDB plugins tend to be smart and they are aware that safe linking exists. So what they will show you may be valid, where what the challenge help text shows you is just like a dumb, naive attempt. No promises there. I know pwn debug does reverse the safe linking in their printout. But for your question, you said I have why what? So I know why. Okay, I'm gonna find out something together here. Gosh dang it, Jeff. Would you believe me if I told you 2 years ago I submitted a PR to fix that? Um, Okay. What you have here, this one has safe linking, so apparently Jeff has no idea where some things are, and it's just lost. What you have here is you have two chunks that are located next to each other in memory. Uh, it may null. Imagine that I have a valid pointer to here. I haven't freed it, but this one has been freed. The distance between these two allocations or two chunks is hex 290. Do you agree? There's going to be a little bit of, I'm assuming that Pwn debug is showing me the allocation pointer. So there's going to be some metadata 8 bytes behind this. But I could overflow from 9B00. I could write hex 288 bytes. Then the next 8 bytes would be my size, right? And then my next 8 bytes would be the next pointer of this freed chunk. And then my next 8 bytes would be whatever is the key. So I didn't like explicitly show it last week, but that was what I was going for when I was saying, hey, we have to malloc free, think about the metadata and think about how things are located next to each other in memory on the heap. I may not be able to write to a freed chunk, but what if I can overwrite from a properly malloced chunk all the way into the metadata of a freed chunk that is after it? You were able to do that. Okay. So you would have to make sure that the T cache, the statement was, so I have this overwrite. I can overwrite this next pointer in your scenario. You know what you want to put there, but I want to put something there, right? And I put it there. How am I able to write to that location? That goes back to the malloc free overwrite malloc. You're doing this same operation. But how am I overwriting the next pointer? And I'm not overwriting the next pointer by a use after free. I'm overwriting that next pointer via a buffer overflow from the allocation that's located behind it. Does that sound accurate? Yeah. And so when you have a use after free, it is just malloc free scanf. All right, malloc, let's go. But hopefully people are, nulling out their pointers. In which case, you do end up with scenarios like that where I have to start caring about where are the addresses I can write to? Do I have the ability to overwrite into the next one? So I'd have to make sure that the T cache has at least two entries. I need to make sure that this chunk is the chunk that is at the head of the T cache. And I would need, so there are at least two entries, and this chunk is at the head of the T cache. This is malloced. I could read into this memory address, overflow this allocation, and overwrite the next pointer here. Then when I malloc, the first malloc is going to return this address. The second malloc would return whatever is written on the next pointer. And at that point, if the program allows me to write, which it has to, because you're using some write to get from here to there, you have the ability to write to, you have arbitrary write to whatever you specified on that next pointer. Uh, Having a hard time. Okay, having a hard time using stack scanf and stack free to get a stack address in the heap. I think it involves creating a fake chunk, but you're not 100% sure. Based on my recollection, you are thinking correctly. Um, so when we free something, how does the thing to think about is how does the Tcache know if it's like a double free? We know that. How does it do it? What does it look at? At some point, yeah, like if you could solve the first 10, you did it. Because there's a challenge that called like Malik and then Malik flag, right? They called Malik twice and it like trolled you. And you had to be like, all right, how do I get the same thing in here twice? Um, so when you free something, the Tcache will look for the key at that address plus eight, right? If it's anything other than the key, you're good. Where was I going with that? Oh, yes, we're doing this stack free thing. So if I want to free something, as long as the key's not there, I'm not going to get the double free error, which is pretty low, right? What are the odds you happen to type this randomly generated key byte sequence? What's the other thing that is used when you free something? There's only what, four metadata values? There's the size that's chilling behind me. Size is immediately behind me. Brief size is before that. Then there is the next pointer. There's the key. There's a whole bunch of space. And then there's the prev size, which is actually my size, right? So if I'm trying to create a fake chunk, those are the only data points that the heap could possibly care about. I would say look at those data points. There's probably like it can't be data behind where I can write, right? That can't be the factor. So what do you need to write to free like an arbitrary pointer? If you're not sure and you want to like discover this for yourself, you're not going to like high level reason it where there's only three metadata values that you possibly could write from a given point. Then try and do it, throw GDB on it, and see where inside the heap it explodes. So when the heap airs, you can step through it and you can find the check that you're failing. And so if you were to like, for instance, read in a cyclic value and then just try and free it, if you're studious enough and patient enough to step through it, you will find the literal compare instruction where the heap is checking bytes of memory in that operation and it decides this is no good, we're going to go abort. And that sounds insanely tedious, but it's a useful skill to have because whatever you learn on 2.31 doesn't necessarily apply to 2.35, which doesn't necessarily apply to 236, and maybe we're on 237, right? And so at the end of the day, unless you're just going to blindly trust what other people say works, you have to discover it for yourself. But you are on the right track there with free chunk. Oh, I forgot. This was an amazing meme. All right, we're animated. We're even doing some motion tracking. And I don't think does it show the byte value? It's we got a win address. Does it say what the one address is? It's another great troll, and it's not like we purposely go out of our way to like make things troll you guys. But there are these sub problems that you encounter in earlier challenges will appear again because they aren't. Yeah, there we go. Uh, hopefully, part of that looks familiar. All right, maybe you cursed with that. All right, these type of things happen in the real world, and so you just need to deal with it. But great meme in particular. I just didn't want to throw it on the slides. With that amount of time, I'm going to cut it. I appreciate everyone hanging out.